Base numbering systems are fun because it's a different way to count. We've been doing all these logarithms with different bases, exponentials with different bases, and it's time to just see what it looks like to change a base in a numbering system. So for that example, if I were to go, well, I'm used to the number, let's say 123. Well, this is my ones digit right here. That counts for ones. This spot right here counts for tens. This spot right here counts for 100s. I'm really used to that in our base 10 numbering system. In a base 10 numbering system, we also have 10 unique characters, the numbers 0 through 9. So base 10 is what we're used to. It has 10 unique characters, and that's all I get. And I know that this is the ones place, the tens place, and the hundreds place. But what you may not recognize is that this is actually 10 to the 0 powereth place. This is 10 to the first power place. This is 10 to the second power place. If we kept going, building it from here, going in this direction, 10 to the third power, 10 to the fourth, but the 10 to the third power, that's the 1,000 place. This is the 10,000 place. And it all flows and makes sense. Therefore, we could do the same thing with any base system we wanted. If I wanted to switch to base 2, for example, I only am allowed to use 2 unique characters, okay, and those numbers would be 0 and 1. And that's the only numbers I can use. Well, it's the only numbers you would use anyways. But if you started here, that first blank in a base 2 numbering system is 2 to the 0 power. That's my 1 position. My next blank is 2 to the first, or the 2's. My next blank is 2 to the second, or worth 4. Then this is 2 to the third, which is worth 8. 2 to the fourth, which is worth 16. 2 to the fifth, which is worth 32. So let's say I had a number like 27, and I wanted to take 27, which is 2 tens and 7 ones in base 10, and I want to switch it into base 2. Well, it's simple. Does 32 fit in? No, 32 does not fit in, so I would not need any of those, so I don't even put anything there. Then I would need 116. A 16 fits in, so I subtract 16, and I'm left with 11. Well, then an 8 would fit in, so I subtract an 8, I'm left with 3. A 4 would not fit in, but a 2 would, and so would a 1. So 27 in base 2 is 11011. Kind of a fun looking number. So you have to set this stuff up every time. Now eventually you're going to have to keep going because the bigger numbers you have, you just keep doubling this. So if I had a number like, let's say I had, well, let me do 30 because it's a little bit bigger. So if I had a 30, I would still need 116. Let me do this in green. I would need 116. I've got 14 left over. So I'm at 14 right now. I could fit one of those in. Now I'm at 6. I'd need one of these, but I couldn't use one of those. So 30 in base 2 is 11110, and that's what 30 is in base 2. Well, that kind of thinking, you can do this with any base then. So if I wanted to do base 3 numbers or whatever, then I can do the same thing. I just go boom, make these blanks backwards just like we do in our own numbering system. And this is worth 1 because it's 3 to the 0 power. This is worth 3 because it's 3 to the first. This is worth 9 because it's 3 to the second. This is worth 27 because it's 3 to the third. This is worth 81 because it's 3 to the fourth. This is worth 243 because that's 3 to the fifth. So if I had a really big number, I could still use it. I could just keep building these until I have enough space. So if I have the number 100, which we're very used to, and I wanted to turn that into base 3 you're going to notice is going to allow us to use 0s, 1s, and 2s. That's my 3 unique characters that I get in base 3. So I will be able to fit an 81 in there. So 100 minus 81 is 19. I've got 19 left over. That means no 27s fit in, but 2 9s fit in. 9 times 2 is 18, and I've got 1 left over. So 0, 1. So 100 in base 3 is 10201, and that's how you make the calculation.